Well, let's see how this goes. Our first equation up here is already of the form y equals. So y equals 4 minus 2/3 x. Where are we going to start on our graph? Four. Very good. So that's our first point. From there, where do we go? Down 2/3. Very good. Number 2 down here, where do we start? Well, that one is not in the form of y equals, is it? So we're going to have to solve that one a little bit. We have to get it as y equals. Well, there's that problem coming back again. So what's the first thing we have to do trying to solve this thing for y? We're going to have to add 1 to it. And when we add 1, and when we add or subtract, we have to do it to only one piece on each side. So adding 1 makes that -1 go away, leaves us with 3y. Where do we add 1 on the other side? To the 5. And if my pen were working, that would be a +5. So +5 plus 1 is +6. What's next? Divide by the 3. Perfect. So y equals, now when we multiply or divide, we have to multiply or divide every digit, every term in the equation. 1/4 x divided by 3 is kind of tricky, but all we have to really do is 1/4 divided by 3, which is 1/12. So that's 1/12 x. Think of 1/4 divided by 3 becomes 1/4 times 1/3, which is 1/12. What is 6 divided by 3? 2. So when we go to graph this, we start at 2, and then from there we go up 1 and over 12. Somewhere in there. A fairly flat line. Oops, didn't mean to take that one away. Number 3. Well, again, we are not in the form of y equals, so we're going to have to do some work with that one. So we have to get y by itself. Where are we going to start with this one? We're going to subtract the 2x to get rid of it, which gives us what? Perfect. -3y equals 3 minus 2x. And then divide by -3. So y equals -1. Very close. Plus 2/3. Yeah, because you got negative divided by negative, so it's a positive 2/3x. So where do we start? -1, yep. And from there we go up 2 and over 3. Perfect. So there we are. And finally, number 4. Where do we start? We're going to subtract the 3x. So we've got 2y equals negative 6 minus 3x. And then divide by 2. Y equals negative 3 perfect. Negative 3 and then minus 3 over 2x. So we're going to start at, when we graph that one, negative 3, yep. And from there we're going to go down 3 over 2. Just like that. What do you think? Still confusing? Okay. Well, today we're going to take a look at graphing in a different way. This was graphing. We're going to look at data graphing. Before we get into that, do anybody have any questions out of the homework they want me to answer? Okay, that's a good sign, hopefully. Sorry, fighting off a sneeze here for a second. I think you're the only one that's speaking up. Do you want me to pick a couple problems out of the homework and work on them, so go through them? Okay. Well, that is very tricky. Though there are two processes that are very, very different. If I say plot the points, and I give you a table X and Y, and I have 3, 7, 1, 4, negative 1, 1. And I tell you to plot those points, well, 3, 7, you're going to go this way first, 1, 2, 3, then up 1, 2, 3, 4, 5, 6, 7. So that's going to be 3, 7 right there. So when you plot points, you go side to side first, and then up and down. 1, 4, you're going to go over to 1, and then up 1, 2, 3, 4. There's your point. That's 1, 4. Because that first coordinate in that point is the x coordinate, or the horizontal. That comes first. Planning -1, -1. So you go to negative 1 positive. You go to -1 and up 1, there's your point. Or if I give you ordered pairs and tell you to plot them. If I tell you to plot, come on. If I tell you to plot 5, 2, well, I go 1, 2, 3, 4, 5, 1, 2, and there's my point. That's 5, 2. So when I'm doing ordered pairs, if I'm plotting points, I have to go over first and then up. This, yeah. Yep, it's always X. In ordered pairs, X and then Y. But if I'm graphing from an equation, I'm graphing a line, like y equals 2/3 x minus 5. There, I start by going up and down first. The -5 tells me from the center I go down 5. That's my first point. Then the number multiplying the x is my slope. That's 2/3. And there I go up and down first. It's a positive 2/3, so I go up 2, then I go over 3. Because it's a rise over a run. So if I'm graphing a line from an equation, everything goes up and down first, and then it goes side to side. So it's just very backwards. That's the part that is very, very confusing about this. Is if you are just plotting points, yes, the horizontal comes first and then the vertical. But if you are graphing, first of all, the y-intercept tells you got to move up or down first. And then the slope tells you that from that point, you go up and then over to get to your other point. What if I ask you something like this? Okay, how about you make completely ordered pairs so that they are solutions to let's see, 2x minus 3y equals 6. So I might give you an ordered pair. Three comma blank. I might give you 2 comma blank. Blank comma -2. Blank comma, oh, let's see here, 0. Well, how on earth would I find out what that other coordinate is? Well, remember, that ordered pair, if it is a solution to this equation, has to make that equation true. The 3 here, does that go in for x or y? X, because it's in the first part of the coordinate. It's always x first, then y. So that goes in for x. So what that's going to be is, instead of 2x, it's going to be 2 times 3. I replaced the x with the 3. And now I can solve that equation for the y. So I'm going to do the 2 times 3 first, makes 6. So I've got 6 minus 3y equals 6. Then what am I going to do? Yes, I have to get rid of the 6. And I'm going to get rid of it by subtracting it. Very good. So I subtract 6, and that's gone. I have negative 3y equals 0. Then what? We'll divide by the negative 3. So the negative 3 divides out, what's 0 divided by negative 3? 0. So to complete that ordered pair, y has to be 0. For this one, we're letting x be 2. So we've got to put 2 in there where x is. So this will be 2 times 2 instead of x minus 3y equals 6. So we'll do 2 times 2 first, which is 4 minus 3y equals 6. Then what? Subtract the 4. So the 4 is gone. I've got negative 3y equals 2. Then I divide by negative 3. I get y equals what? It's negative 2/3, yep. For the next one, it's not x, but y that we're given. Y equals negative 2. So I'm going to write that as 2x is going to be there, but it's minus 3 times y. So 3 times negative 2 goes in for y. Equals 6. So now I'm going to combine. I'm going to treat this as a negative 3 times negative 2, which is positive 6. Then what? Subtract 6. Two x equals 0. And finally, divide by 2. 0 divided by 2, of course, is 0. So x is 0 there. So that's 0. This one will do the same thing. We'll put the 0 in for y. So 2x minus 3 times 0 equals 6. I'm going to give you guys a second to solve that one in your notes. What'd you get? X is 3. Very good. Up here we had when x was 3, y is 0. So the opposite has to be true. When y is 0, x has to be 3. Okay, so let's say I take an equation. Y equals 2x minus 5. And I ask you, plot 3 points or 3 ordered pairs, and then graph the line. So that's different than what we've done. So far, we've just been looking at the equation. This one would start at negative 5 and then go up 2 over 1, right? But here's asking us to plot 3 ordered pairs. To plot 3 ordered pairs, that's going back to just making a basic table. And we're going to pick values for x. I might pick negative 2, 1, and 3 as my values for x. They may ask, where did those values come from? I flat out just made them up. It doesn't matter what values you pick for x, as long as they're on the graph. A lot of times my math app will give you a 10 by 10 graph or an 8 by 8 graph. If you pick a number that's off the graph, obviously you can't plot it, but it has to be on the graph. I like to pick some negative values and some positive values. That's why there's a -2 in there. I like to spread them out a little bit. So now if x is -2, what's y have to be? Y has to be 2 times -2 minus 5. Well, 2 times -2 is a -4. Minus 5 is a -9. So that gives me the ordered pair -2, -9. Now, if the graph goes is 10 to 10, both axes, then we're okay. If it's an 8 by 8 graph, we can't fit that on there if it only goes to -8. We would have to get a different number for x. For this case, let's say that we do go up to 10 by 10. So -2 or 9 is somewhere in there. So there's my first point. If x is 1, y is 2 times 1 minus 5. 2 times 1 is 2. Minus 5 is -3. So that is the point 1, -3. So there's +1, -3 is right there. So even though we're graphing, we're really just plotting points. So that's why we go side to side first and then up and down. And then finally, 3. If x is 3, y is 2 times 3 minus 5. Well, what is 2 times 3? 6 minus 5 is 1. So that gives us a point 31. So that's right there. 31. There's our line. Now, if we'd use our shortcut, we'd be starting at -5. And this is, we treat this as 2 over 1, so we go up 2 over 1. We get the same line, right? But I said my math lab sometimes specifically wants you to plot those points. So you just got to click those 3 points on the graph and then stretch a line through.
On 3 points, it would only let me plot 2. So to do the line, you have to do the first one and the last one. That's where I got confused.
Oh, sure.
Just plot 3 points, but it only lets you do 2.
Yeah, I was getting frustrated with that too. So.
Yeah.
Okay, let's see. I've got one of them up here. Let's see what it lets me do. So -3x minus 6. So if I use 0, 6, see what's my dot tool, that circle tool. Oh, sure, yeah, it's only going to let you do
2.
Yeah. So I would just pick the first one and the last one to plot. I was getting confused. I didn't know what it was telling me to do.
Yep, they're just telling me we need a third point.
Yeah.
Let's do an example and see what it does for us. Doesn't show us how to use the thing. Well, let's see. Huh. This is an upgrade on my math lab from last semester, so this pallette's a little bit different than the one they had last semester. And I am not. Let's try this.
I think if I just plotted the first one and the last one with that line tool, then it would mark it right, but I still plot 3 points and it's in.
Okay.
You try one, you try to do it, and it's just like, and then you try to do the other one, it's just like, really?
Okay, yeah. It's marking it right if you just do 2 points. But it's not.
Yeah, you're not, if you can't follow the directions, it says no.
Yeah, that's weird. Huh. Well, I guess if it does that on a quiz, let me know. And I'll make sure it gets changed on your grade. Yes, that is. I might be a little bit obsessed with making it work now. It keeps marking it right, but it's not. Oh well. Okay, I'm gonna shut up and let it go, or I'm gonna sit there all hour looking at the thing. Ah. How do I graph that?
Down 3 in the center.
Down 3, okay. Draw a flat line. This is a horizontal line. Y equals is a horizontal line. X equals 5. What's that going to look like? That's going to be perfect. I go over to x equals 5, and there is a vertical line at that point. At x equals 5. Okay. Well, our new stuff for today. We're going to start looking at data graphs. In a data graph, we're looking at displaying sets of information that we have gathered. The graphs we've done so far represent what's called a function or a relationship, that equation, in other words. Well, data doesn't always follow a perfect pattern, a perfect curve like those numbers do. It can't always be described with an equation. So one of the data graphs that we are going to look at, well, there's going to be 2 types of graphs that we're going to look at. There's going to be what's called the numerical, sometimes called quantitative. Quantitative just means dealing with quantities or numbers. So what we're doing is what we are graphing are numerical results. The other type of graph we're looking at is categorical, or sometimes called qualitative. Qualitative or categorical is displaying a quality of something. Or it puts you in a category. An example of a numerical thing would be Age. We gather the ages of all our students and then graph the ages to display the ages. That's numerical. Categorical might be favorite color, or what program, what major are you in? Are you business, trade and technical, liberal arts? What programs are you in? So that puts you into a category. What's happening with all of these is we are asking a question. There is a variable that we are graphing. It's called the random variable. And the random variable is the answer to a question of interest. That question of interest might be, do you receive financial aid? The answer to that question is either going to be yes or no. You either receive some or you receive none. That is a categorical. Because it puts you into the category. Either you put into the category of students who receive financial aid or students who do not receive financial aid. If I ask how much financial aid you receive, that is a numerical question. It's creating a numerical random variable because the answer to that question is going to be a number. Now, if you don't receive financial aid, that number might be 0, but it is still going to be a number. So let's start out by taking a look at the categorical data. Categorical data, categorical random variables, again, come from the answer to that question that puts you in a category. Any yes or no question is categorical. And what's your favorite color? What program are you in? What's your major field of study? What city do you live in? Things like that, where the answer puts you in a category. So let's look at a simple one like favorite color. And let's say I'm going to answer that question of what is your favorite color. I'm going to give you 3 choices: blue, red, or green. And I'm going to make everybody choose from those 3 choices. So since we've got a small class here, I'm just going to make up numbers from a larger group. So let's say we have red, red, blue, red, green, red, blue, blue, green, blue, red, green, green, blue, green. How many do I have there? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. Perfect. We'll go with that for that first row. Let's do red, green, red, red, green, blue, blue, green, blue, red, green, blue, green, green, red. There are 30 responses listed there. Looking at that list, can you tell me, without counting anything, can you just look at that list and tell me which color was the most popular? Now, I could ask that question. I mean, I put those results in there in a very specific way. I could ask that question of a dozen different people and probably get 3 or 4 of each answers to each color. The reason being is the human brain is only capable of comprehending, of storing about 7 to 13 items at a time. So when you look at this list, you cannot see and really take in all 30 responses at once. So you might look at it and look at here. If you're looking at this section here, what appears to be the most popular answer? Red. Look at this section here, what appears to be the most popular answer? Very strongly blue. How about down here? Most likely green would be like what you would consider to be the most popular answer there. So we don't want to leave this based to just our perception looking at these colors. We want to be able to organize them somewhere. The first way we are going to organize them is into something called a frequency table. And what a frequency table does, it just breaks things down. In categorical data, it's very simple. You're going to list your category in the left-hand column. In this case, it's color, so I'm just going to title that color. I have red, blue, and green. Let's count how many reds we have here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. You are absolutely correct. That column is called the frequency. That tells us how many times they occur. I can count the blues. 2, 3, 4. Comes up with 9. Okay, I'll trust you on that. Then the greens must be 11. Now, rather than going through and counting like I just did, what we could have done is we could have done an extra column called the tally column, where we could have gone through and just said, okay, the first one's red, so there's a check mark for red. We got red, blue, red. So red, blue, red. Green, red, blue. Green, red, blue. Blue, green, blue. Blue, green, blue. Red, green, green. Red, green, green. You guys get the picture, right? You can put that tally column in there, but in your finished graph, of course, that wouldn't be a part of it because that's a working column. You take it out, that's not part of the display. What you're really displaying is just this right here. The colors, the categories, and the frequencies. This can now be displayed in a couple of types of graphs. One would be a bar graph. A bar graph can be either vertical or horizontal. In statistics, vertical is more common. So in a vertical bar graph, the categories go along the bottom. In this case, our categories are color, so we're going to call those color. I'll label it red, blue, green. Going up the left side, then we need some sort of a number scale. We have to be able to get up to our largest number, which is 11. So I have to make sure I number this high enough to get up to 11. So I'm going to go 2, 4, 6, 8, 10, 12. Notice I didn't have to go by ones. I went up by twos to make sure I got there. If I'd went up by ones, those lines would have been really close together. It would have been kind of cluttered. Also, notice I didn't number every line. That would have made it kind of cluttered as well. So red was 10. So I'm going to draw a bar above red. Blue is 9. So I'm going to draw a bar above blue to 9. Green is 11. So I'm going to draw a bar above green that goes up to 11. If it was a horizontal bar graph, I'd do the exact same thing. Well, now the colors would be along the side. And it would be numbered on the bottom. And then, of course, the bars would go horizontally. Now, one thing I was trying to be careful of here, and I didn't do such a great job in this second graph, was I was trying to be very careful to make those bars all the same width. Because one of the tricks that get used is something like this. If I look at that graph and I ask you which color is more popular, which one would, at first glance, without looking at the numbers, what would you say? Red, because boy, that bar is big. But if we trace it down here, that only comes to the 10, doesn't it? The green bar is longer. So that's one thing that can be used to make a graph deceiving, is varying the width of the bars. Notice I also avoided the colors red, blue, and green here. I'm purposely did all of them in the same color. All the bars are black, all the words are written in brown, because that's another thing that can be used. Even if the bars are the same width, if I color that one in red, this one in blue, and this one in green. Now those are all very, they're primary colors. They're all very dominant colors. So you still look at it and you still see the green one's taller. But if you have a lot of bars, there's only 3 here, so you can see them all kind of at once. If you have a lot of bars and you have some red, some blue, some green, the red ones will often tend to stick out. So if they're far apart, there's 2 of them that are close to the same length, the red one will look longer. Also, if I had done the whole graph in blue instead of brown and black, well, even though you see it's labeled green for the longest bar, you see the color blue, and in your mind, you're more likely to associate blue with that. So there's a lot of things like that that are done to make these graphs deceiving. Another thing that can be done to make this graph deceiving is this. That is a perfectly accurate graph, but it looks like green is like 3 or 4 times as big as the blue. Why does it look so exaggerated? Because this little hash mark on the axis, I cut off the axis. I didn't start at 0 and number up. Now this is just fine. You are allowed to do this little hash mark on the axis and skip numbers, but be aware that it can be deceiving. And this is what companies will do. If instead of colors, if this was companies A, B, and C, Company C might put out this graph that makes it look like they're way ahead of the other two companies, when in reality up here they're all very, very close and it's just slightly ahead. So a lot of things that can be done with these graphs to make them deceiving. Well, on this frequency table, I'll get rid of this tally column, there is another way the data can be broken down. And that is what we call relative frequency. Relative frequency is a proportion, similar to a percent of the time that a thing occurs. To do relative frequency, the first thing we have to get is a total. Well, if we add all these up, we get a total of 30. So now our relative frequency is found by taking the frequency divided by the total. So for red, that's 10 divided by 30, or 0.333. I am choosing to round to 3 decimal places here. We could round differently depending on what the data is. Blue is 9 out of 30, or just 0.3. And green is 11 out of 30, which is 0.367. What should those numbers there all add up to? 1. Because the total of 30 divided by 30 would be 1. Or 100% is kind of what you were thinking. And it adds up to the whole thing, 1 or 100%. And there's also something called percent frequency, where you just move the decimal point and make them percents. And they would add up to 100. So this would be 33.33%. This one would be 30%. And this would be 36.7%. I have to put an extra 3 there. And of course, those better add up to 100%. Now, what if they add up to 99.9 or 101 or 100.1? That's just round off errors. Because you see 2 of these percents had to be rounded off. Yeah, this is 0.333333333. This is 0.3666666. 2 of them had to be rounded off. It just happened that they still worked out. But if you're dealing with more than 3 or 4 items, sometimes that round off error will make it not perfectly add up to 1 or 100%. As long as you're really, really close. Now, the big thing this relative and percent frequency is used for is another type of graph called a pie graph, or sometimes referred to as a circle graph. And sometimes not just called a pie graph, might be called a pie chart, depending on what you're doing. So, years ago, what we would have done to make a circle graph or a pie chart is we would use a protractor to make our circle perfectly round. And then, how many degrees are there in a full circle? 360, right? So we would have found 33.3% of 360 is 120 degrees. We've taken our protractor and measured out 120 degrees and made it nice and perfect. Well, we don't live in that world anymore. So if we look at this, what's half a circle equal to? What percent? 50%. Yeah. Quarter of a circle is 25%. Of course, I'd keep cutting that in half. That would be like 12.5% and so on, right? Well, up here, we've got 33.33%. That is basically 25 plus 8, right? A little bit less than 25 plus 12. So I'm going to take my quarter circle and then probably somewhere right about there. That is my red. Green is 36.7%. That's 25 plus 11 or 12, right? So that would actually be the whole all the way up to that quarter. That half of a quarter, right? That's my green. And blue has to be what's left. Now it looks like it's slightly more than a quarter circle. It's slightly more than 25%. 30% is what it is. So there's my little circle graph. Now that seems very quick and sloppy, and it kind of is. But in today's day and age, if I wanted a perfect, beautiful circle graph, there's so many computer software packages out there that'll do it for me, like Microsoft Excel here. I make my little table. I highlight the whole table. I go to Insert. Go to Charts. Here's Circle Chart, Pie Chart. I can pick whichever style I want it to be. That one makes the most sense. That one wouldn't be terrible. I use a donut chart. I'm just going to do a simple circle chart right there. Now this one has a key. You can click on it, add data labels, puts the numbers in there, format data labels. You can put the series name, category name, all sorts of different things go in there. You can get percentage. You put all sorts of different things in your graph. And you got a nice, beautiful graph. Now I misspelled green there. That was unfortunate. There. You can also, I'm not going to take the time to do it, but you can also edit the colors and stuff like that here too. I'm not going to get into that, but yeah, you can edit everything you want on here and make it nice and pretty. So really making a very accurate circle graph by hand is not a necessary skill anymore. Okay, so those are the two main types of graphs for graphing categorical data. There's another type of graph that is used, but you're going to hear me say bad things about it right now. That's called a pictograph. A pictograph is basically to deceive. I mean, they use them in magazines and stuff like that because they're pretty. They look good on the page. Maybe a little bit of entertainment value. But they're hard to read, and we talked about things you can use in the other ones to be misleading, like changing the width of the bars and colors of the bars, and arranging them in different orders or whatever. In a pictograph, it's extremely easy to be deceptive. Like if I wanted to do a pictograph on how you get to work in the morning. How many people drive themselves? And over here in my key, my legend, I might have a car equals 5 people. So something like that. What does that represent? 5, 10, yeah. 13 or 14 is what it looks like, right? Can't tell for sure whether it's 13 or 14, but we know what's in there. I'm going to call that one 14. We might have those who ride the bus. Over here in our legend, might have bus equals 10 people. Well, what's that stand for? 21, 22, somewhere in there. We'll call it 22. But you notice it doesn't take up any more space than the 3 cars with the 14 people. Might have those that bike. Might have a bike equals 2 people. So what's that mean? 2, 4, 6, 8, and another one would be 9. You can see what's going on here. All of those are coming out almost in exactly the same spot, but they have different values. The picture's giving me. Now, this is an extreme example of a misleading pictograph. I can grant you that. But, somebody who's, let's say, they're trying to lobby the city to put more money into bike paths and to take money out of, the bus service, public transportation. They might be making that argument of there's just as many people riding their bikes to work from this graph as there are people riding the bus. So we should be putting equal amount of money into maintaining bike paths and bike trails as we do in the public transport, the mass transport. Other things, like I showed, technically, if I change the width of the bars, that's not a bar graph anymore. That would become a pictograph too. A bar graph has to have the same width bars to be considered a bar graph. Another way that I've seen a hybrid graph, it's, like I said, it's a bar graph that's turned into a pictograph used, might look like this. Well, looking at this, it looks like C is way, way larger. But in reality, what matters is simply the height of the front of the box. Well, A is 2, B is about 2.5, C is like 3, 3.25. So it's not that much larger. It's just because that second and third dimension added into it, it makes it look tremendously larger. So things that can be deceiving. I'm going to cut off the first hour there. And when we come back from break, we'll talk about numerical graphs. I might give you an extra credit question to try again.